Factorials count the number of ways that we can order a set of distinct items, and permutations count the number of ways that we can order a subset of distinct items. But sometimes we don't actually want to order a subset that we're taking. Sometimes we have a collection of items and we want to grab a subset, but we don't care about their ordering. We don't differentiate the positions that they're in. And so we might be interested in knowing how many ways can we actually do this? How many ways can we select a subset from our total without concern for what the ordering actually is? And so if we're faced with a situation where we need to select a subset and we are not concerned with the ordering, the total number of ways that we can do this is referred to as a combination. So what is our motivating example here? Well, suppose that there are a total of 10 books that we have, and we want to carry these in our backpack or in our book bag, but we're only going to be carrying 5 of them. So how many ways are there of us carrying 5 different books in a bag where, of course, because they're just being thrown in our bag, the order that they're put in there does not actually matter? So if we had taken the factorial, that would tell us how many ways we could order all 10 of them, right? 10 factorial gives us those orderings. Permutations would give us the ways that we could order the subsets of 10 of those books, right? But again, we don't care about the ordering here. But perhaps we can consider the permutation to be motivating this, right? With our permutation, we can think about taking the subset of our 5 books and then choosing the way that we order them. Right? And if we break it down into that 2-step procedure, we notice that if we just ignored that second choice that we're taking, well, then we'd have what we want, right? Because we select a subset of 5 items, and then we order that subset of 5 items. And so if we just simply ignore the ordering, well, now we have our subset of 5 items. All right, so we select our 5 books without ordering, then we order those 5 books. And so if what we really want to know is how many ways can we select those first 5 books, well, we can actually turn towards the product rule for counting, right? Because what we can say here is that we know that the total ways of doing our permutations is our permutations with a total of 10 and a 5. And what we can say is that, well, divided into 2 different steps, there are m ways of doing step 1, right? And m is ultimately the number that we want. We want to select 5 books without ordering. There are 5 factorial ways of ordering the 5 books that we've selected, right? And so what we can say, therefore, is that m has to be the permutations divided by 5 factorial. And we worked out the permutations to be 30,240. 5 factorial is 120, which means that m has to be 252. Right? So in other words, if we just start from the fact that the permutation can be thought of as this 2-step procedure, and then we rearrange by bringing our factorials over to the other side, right? Then what we're finding is that m has this general formula that we can actually work out. So there are 252 ways of selecting 5 books out of our total of 10. Okay? This is using our product rule for counting, but we're using it in reverse, right? We're not knowing all of our orders. We know the total number, right? So we know our total number over here, and we know different numbers throughout the procedure, but we're solving for one of our unknowns, okay? And so that's how we're using our product rule for counting here. So how can we make this into a general rule? Well, in general, if there are n distinct items and we want to select k of them, but we don't want to put them in order, then our combinations is going to count the total number of ways of doing this. In terms of the notation that we're going to be thinking about for combinations, we typically are going to use this binomial coefficient notation right here. Okay, and so the way that we would read this out is we'd read this out as n choose k. Importantly, there is no division line here. This is not division. This is telling us that we need a combination here, right? So we put these rounded brackets, and then we write n over k inside of the rounded brackets. If you'd prefer, you can also use notation like this, which has the c total of n choosing out k, right? That's sort of reminiscent of the notation for permutations over here, okay? But either way, whatever notation you're using, okay, the ultimate idea is that we're going to take the total number of permutations, divide that by k factorial. If we write that out in full, the permutation is n factorial divided by n minus k factorial, and so our combination is going to be n factorial divided by n minus k factorial times by k factorial. Okay, so it's the number of permutations divided by k factorial. Okay, and so that ultimately is going to give us this. Again, if you read this out, then we're going to say n choose k, or n combinations of size k. Combinations of size k out of n. Now, notice that if we take the cnn, or n choose n, this is going to be equaling 1. since n minus n factorial is equal to 0 factorial, which is 1, right? And so if we look through what we're doing here, right, k is equal to n here, k is equal to n here, right? And so this n factorial and this n factorial will cancel with each other. N minus n factorial, 0 factorial, which cancels out, right? So everything's canceling down to 1 there. In other words, if you have n items and you want to take a subset of n of them, how many ways are there of doing that? Well, there's exactly one way, because you have to take all of your items. Okay. Now, with combinations, the order does not matter. We're not going to be thinking about ordering them. You can't distinguish the items once you've selected them out. If you care about order, we're going to be turning towards permutations or factorials. If you don't care about order, then we use combinations. The combination can actually be derived by thinking about the permutation and then ordering it. And so there's this relationship between these two different ideas here, right? We can link up our factorials, our combinations, and our permutations all through our little formula there. So let's take a look at some examples and consider here that we're choosing cards from a deck of 52 cards. So how many different hands can we pick that have 5 cards in them, right? There's a total of 52 cards. We want to choose 5 of them. It's a deck of card hands. We're not thinking about our hand ordering mattering, so it is a combination. We use 52 choose 5, which gives us 2,598,960. Now, I will point out at this point that with our combinations, we of course can express them all in terms of factorials, but if you're wanting an actual numeric value out of them and you're using your calculator for this, your calculator is going to have a combinations button. It's probably a big C, and so if you're not entirely sure how to enter it on your calculator, then you should look up your calculator's manual or search online for how to do that, but your calculator will actually be able to do these expressions numerically. Now, Part B, how many more 7-card hands exist compared to 3-card hands, right? And so if we wanted to know this, we need to know, well, how many 3-card hands exist? We need to know how many 7-card hands exist, and then take the difference. But of course, to calculate how many 7-card hands exist, we're doing basically the same thing we did in Part A, except instead of 52 choose 5, we do 52 choose 7. Same thing with 3, right? And so we could say that there are 52 choose 7 total 7-card hands, and 52 choose 3 total 3-card hands. And so if we take the difference, that gives us 133,762,460, right? So there are quite a lot more 7-card hands than there are 3-card hands. How many different 5-card hands contain only hearts? Okay, so now we're getting into a slightly more interesting question here, right? Where instead of us thinking about there being a total of 52 items that we want to choose from, we can only choose hearts. And if we think about, well, how many hearts are there in a deck? There are 13 of each of the different suits in a deck of cards. Okay, and so what we're really doing is we're picking 5 cards out of a total of 13. We don't care about the ordering, so we're dealing with a combination here. And so then 13 choose 5 is going to give us the relevant answer here. So that's 1,287 different ways that we can take 5 cards that are only hearts. How many different 5-card hands contain only 2 suits? Okay, and so again, we can think about the way that we might do this here, right? There are a total of 4 suits and we want to choose 2 of them to use, right? And that's sort of our first step. And once we've chosen those 2 suits, maybe we're doing hearts and diamonds, or we're doing clubs and spades, or we're doing clubs and hearts, right? Whatever 2 suits we happen to choose, there are going to be 26 cards in the deck that satisfy those 2 different suits. And so what we can think about this is as a 2-step procedure. First, we pick which 2 suits we want to use. Second, we pick of those 26 cards that are valid from those 2 suits, what 5 are going to be in our hand. And so 4 choose 2s gives us 6 total pairings of suits. 26 choose 5s gives us 65,780 hands using only those 2 specific suits. And so then 6 times 65,780 gives us 394,680 different hands that contain only 2 suits. Okay. Now, consider what would have been different here if we had wanted exactly 2 suits. I'll leave this as an exercise for you to think about, right? But in this answer here that we're giving, you might end up with a hand that contains only 1 suit. And so how might you go about eliminating all of the hands that contain only 1 suit in this way? Okay. Moving on here, how many different hands of size 5 contain exactly 2 aces? So we want exactly 2 aces. There are 5 cards total in our hand. And so what do we need to do? Well, first we need to think about how many ways can we pick out 2 aces, right? And there are 4 aces in the deck. We want to pick out 2 of them. So that's going to be 4 choose 2. But then we need to fill out the other 3 cards that are in our hand still. And so we have to think about what cards can those be. And the only thing that we know is that those cards cannot be aces, right? There are 48 cards in the deck that are not aces. And so then we need to choose 3 more of those, right? So there are 4 aces, 4 choose 2 equals 6, gives us how many ways we can pick out 2 of them. 52 minus 4 gives us our 48 non-ace cards. So 48 choose 3 tells us the number of ways that we can pick 3 cards that are not aces. Okay, and so now we've picked our 2 aces, we've picked our 3 non-ace cards, multiply those 2 things together, gives us our total of 103,776 ways of picking exactly 2 aces within a hand of size 5. How many different hands of size 5 contain exactly 3 denominations? Okay, so this is going to be a little bit more tricky, right? Because not only do we need to know which denominations we're going to pick, but you need to have at least one of each of these denominations. But if you do that, you're only going to end up with 3 cards. And so we know that there has to be some replication. So how might we start breaking down this question? Well, there are going to be 13 choose 3 ways of choosing our 3 different denominations. So we start by saying, what 3 different cards do we want? Do we want aces, 2s, and 3s? Do we want aces, kings, and queens? Do we want 7s, jacks, and 2s, right? Whatever, right? We choose 3 of our different denominations. That's our first step. And there are 286 different ways that we could have 3 denominations represented. But then what we recognize is that we either have to have 3, 1, and 1 in terms of the duplicated cards. So 3 of one type, 1 of the second type, 1 of the third type. Or we need to have 2, 2, and 1, right? 2 of the first type, 2 of the second type, 1 of the third type. Now, I encourage you to convince yourself that these are the only ways of representing these. And of course, it doesn't matter which of these are going to be, right? We'll need to take that into account, but it's either 3, 1, 1 or 2, 2, 1. It could be 1, 3, 1 or 1, 1, 3, but we'll take all of that into account in a moment here. So if we have our first type, right, then what we are going to be able to say is that we have to take our, decide which of our suits is going to be the one that we have 3 of a kind of, right? So there's 3 choose 1 ways of doing this, right? So this takes into account, well, which of them are going to be duplicated 3 times. And then we need to say, well, there's 4 of those cards. We need to choose 3 of them. And for the other 2, there are 4 choose 1 and 4 choose 1. Okay, and so what this is telling us is that there are 192 hands once we've picked out our 3 specific suits, or our 3 specific denominations rather, that are going to meet this 3, 1, 1 pattern. We pick out which card is repeated. We pick out how many ways there are of choosing 3 of the 4 of those, how many ways of choosing 1 from the 4 and 1 for the 4 for the other 2. Okay, so then we can do a similar thing for our 2, 2, 1, right? Except what we need to do is we need to say, well, 2 of them are being duplicated, right? So we 3 choose 2 tells us which ways there are of what of the 2 should be duplicated. And then we need 4 choose 2, 4 choose 2 for each of those, 4 choose 1 for our last one. Okay, and so that's going to give us 432 sets of this. Okay, and so then we bring this all together, right? And what we say is that there are going to then be 286 ways of picking out our suits, okay, or our denominations. There are 192 of the first type, 432 of the second type. We add those up for all of the hands that are valid, multiply those through by a product rule for counting, and that gives us 178,464. Okay, and so I'd encourage you to pause and sort of really think through this example and make sure you understand the breakdown of the argument here. At every step, we're just using combinations. However, the way that these combinatorics problems can start to get really challenging is by recognizing that the way to break up the question is not always going to be obvious, right? And so we need to think of ways of actually breaking down the problem so that we can use our tools. And the most effective way of learning how to do this is by practicing this a whole bunch, but also making sure that you always understand exactly what's going on in the argument. Right? So we're thinking about this problem by first picking out the denominations. Once we pick out the denominations, we recognize that there are 2 different ways that we can form valid hands. And so we count up how many valid hands of the first type, how many valid hands of the second type, combine all of that together with our product rule for counting. Right? These are not necessarily easy questions to work through, but hopefully if you break down them step by step, it becomes easier to work with. As a totally separate example here, right? Suppose that we have 45 people who are running for general positions in our student government, right? So there's not specific positions, they just are running to be on the student government. If the government has 10 representatives, how many ways can the government actually be formed? Right? So we have 45 total people, we want to choose 10 of them, right? 45 choose 10 gives us our total number of ways of doing this. Okay? Now, if the government has 3 different groups, each group has to have 3 representatives, how many ways can the government be formed? Okay, and so there's going to be a couple of ways of thinking about this, but I think that the easiest way is to actually treat this as us picking out 3 different subsets, right? So we want to pick out our first subset, then we want to pick out our second subset, then we want to pick out our third subset. So for the first subset, we have 45 people, we want to choose 3 of them, 45 choose 3, easy enough. For the second subset, we no longer have 45 people though, right? Because now we've already picked 3 of them, they're in our first subset, and so now we only have 42 people left. We have to choose 3 of those, and then we're going to have 39 people left, right? So we can take 45 choose 3 times 42 choose 3 times 39 choose 3, and that will give us our total number there. Now, if the government's going to have 10 representatives, and then a subcouncil will be selected of size 4 from those 10, how many ways can the government actually be formed? Okay, and so how can we do this? Well, first we want to pick out which 10 people are going to form our government, right? And so that's 45 choose 10. We've already seen that before. But then we need a subcouncil of size 4 selected from those representatives. And so then we have 10 individuals. We want to pick 4 of them, and that's going to form our subcouncil. And so we take 45 choose 10 times 10 choose 4. Break that down. That gives us our total number over here. Alternatively, you could think about this as choosing 45 choose 6 to take the people on the government who are not a part of the subcouncil, and then there's 39 remaining people. We want to choose 4 of those in order for them to actually be on the subcouncil. That will give you the same response. So combinations are going to count the number of unordered subsets of items from a group. The number of options can be derived using the product rule for counting, as well as permutations and factorials. Right? They're all deeply related to one another. Oftentimes, what we're going to find is that counting problems can be solved using either permutations or combinations, or perhaps even factorials. We're often going to need the product rule for counting. And so as we start to build up our toolkit for solving these types of combinatorial problems, the problems can get quite complex. And so the best advice that I would have for you in trying to solve through these problems is to really try to break this down step by step. Try to come up with an equivalent situation where what you're doing is going to end up with the same result at the end, but every step of it is easier to do. So instead of thinking about forming your council all at once, think about forming the subcommittees one step at a time. It's going to give you the same total number, but it becomes a lot more obvious what you're supposed to actually be doing. And of course, in order to become an expert at dealing with these types of problems, you're going to need to practice them many times over. And so take a look at the examples throughout the lecture, but then also consider trying to solve some of these problems on your own as well. And as you start to work with these ideas should become easier and easier to continue working with into the future.